Okay, so couple of big themes that I think that we see that you should pick up on our discussion of birds. In what ways are birds like reptiles? Sasha, you should jump in at one of these, because yesterday I saw you experiencing that firsthand. They have scales on their feet, right? You can look at these things. They're very reptilian in that the scales, right? There's a lot of other skeletal things that sort of suggest a reptile ancestry. They lay eggs, right? So they're oviparous. There are no viviparous birds. The fossil record suggests this. We're going to look at some of these dinosaurs that had feathers. Right? It's kind of pretty fascinating. But in what ways are birds like mammals? In what ways are birds like mammals?
Yeah, smaller feathers like fur to keep them warm.
Okay, so those little down-like things. So they have these keratinized. So really, this is keratin. This is keratin, right? So it's amazing, right? You have, no, if there was, it'd be perfect if there was a snake sitting here. But scales are made of keratin, right? So the genes for scales, feathers, and hair are pretty similar, right? It's the same type of material. And what's keratin? It's a type of protein. So there's these cells that produce that protein, and they give you hair. So, okay, that's true. Okay, what else? What about their hearts? How many chambers? How many number of chambers in a fish heart?
Oh, fish is 2.
2. Okay, amphibian.
3.
3.
Turtle.
3.
Snake.
4.
3.
Oh, 3. Oh, okay. Crocodiles have 4.
Crocodiles have 4. Mammals.
4.
What about birds?
4.
They do. We do have 4 chambers. 2 atrium, 2 ventricles. Right? That's kind of. What about endothermic, ectothermic? Endothermic temperature on the inside, ectothermic temperature from the outside. What about birds? Endothermic or ectothermic? Endothermic. What about mammals? What about all the rest of the reptiles? And all the amphibians and all the fish? They're all ectothermic, right? So in some ways, this is real similar. Mammals and birds are real similar, but we know that those things are homoplasious. Homoplasios, i.e., right? If we look at the way that the amniotes are broken down, we have this branch, the synapses. Leading to the mammals. And over here, we have the anapsids leading to the turtles. And we have this one. What's this one? Synapsids, diapsids. Or wait, I just said it. Diapsid. Good. Okay. Diapsid leading out here. And what's on the diapsid? Right. Diapsid. Which type of living vertebrates have 2 fenestral openings? Okay, so those are the lepidosaurs. Lepidosaurs, and that includes the tuataras and the squamates. We'll just put squamates. And then we have the archosaur lineage. That includes crops and Aves, the birds. Okay, so again, it's clear, it should be clear looking at this phylogeny that four-chambered hearts arise here, and then they arise over here. Endothermy arises here, and then it arises again over here. Well, actually, over here. Right? So this is not common or similar by inheritance, it's similar by convergent evolution. They both independently evolved just very distinctive four-chambered hearts. They both have four-chambered hearts, but a mammalian four-chambered heart is very different from a bird mammalian heart. Oh, bird four-chambered heart. Okay. So that's something that's kind of very curious to me about birds and mammals. They're always kind of grouped together because they're endothermic. Very, very different from each other. Okay. Very different from each other. And so there's some question about this. Why did endothermy arise in birds? What are some benefits of endothermy? What are some benefits of endothermy? What's some benefits and some drawbacks? What's something good about maintaining 98.6 degrees? Yeah, but why? Well, who cares? Why is it beneficial?
You don't have to hibernate.
What's that?
You don't have to hibernate.
But mammals do though.
True.
You don't have to like sit out in the sun. I guess like because like don't they like sit out in the sun to maintain body heat?
Okay, so behaviorally,
And
as opposed to a snake has to spend a significant amount of its time budget to
So then
To
like yeah, 'cause they could be
thermoregulate.
spending that time like
Okay.
hunting or like
Wake up in the morning.
also
Ready
protection.
to
Like
go.
you're not just sitting out in the sun.
Okay, so that could be, yeah, so you could hide and still maintain your temperature. That's a possibility, yeah, it's a good
Could
hypothesis.
be flying, like it's too cold flying.
Oh, so birds, okay.
Yeah.
So they would not be able to be ectotherms if they're like flying through the air. Yeah, that's a good question too. So I think there's a couple things going on with flight. One is think of how much energy it takes to fly, right? And what's the relationship there? Okay, I'm gonna draw, this is like Pictionary. Okay, let's see. Bean shape, it has membranes. Membrane is folded into these stacks of things. It takes glucose. Oh my God, mitochondria. Okay, mitochondria. So it takes glucose and it takes oxygen and it outputs CO2 and it outputs ATP and it outputs water, right? But more importantly, or in this story, where does the heat come from? When glucose is changed into ATP, just like when gasoline is changed into kinetic energy, there's some waste. And what's that waste given off as? Heat, right? It's not a perfect conversion. And so that's where our body temperature comes from. So in other words, it takes a lot more glucose an endotherm because a lot of our glucose is burnt up and given off as heat. Why? So we can be 98.6 degrees. Okay. But think about how much glucose it takes for a bird. Say what does a hummingbird eat? They eat straight glucose. Why? Because it takes so much energy. And all that energy, all that ATP that's generated gives off a lot of heat.
Even for migratory birds, they have to fly like pretty much the whole life.
Incredible. There's some evidence that they're flying, then they'll stop at a patch for a few days, and while that they'll maybe gain 20% of their body mass back just in a few days, eating as much as they possibly can, and then they take off again. There's some theories or hypothesis that it's related to your immune system too. Right? If you can maintain your body temperatures a little bit higher, kind of like fever, right? Then the environment's usually a little cooler than us, right? So the environmental bacteria can't just hop into our body because it's too hot in there. Okay, that's another idea, right? But regardless, we get this in both, and in fact, both mammals and birds. We get a high metabolic rate, and we get form of insulation. In mammals, the insulation is in birds, the insulation is feathers, right? You think about a down jacket, they're really good for insulation. So you see these kind of correspondence between these things. The question is, I guess, which came first, right? Was it the elevated metabolic rate? Or the insulation? Is the insulation in response to being more efficient? Just kind of trap and keep that energy, right? But of course, nobody really knows. I mean, we could look at a phylogeny and say, right, crocodiles are obviously not endothermic, so it must have arisen at least here. But there's been a lot of speculation about. So what else is in this? If we just focus in on this little branch here, what's not drawn on here that's actually there in the article? So we got the living crocs. Then we've got these branches here. What are those branches? What are birds split from that are extinct? Dinosaurs, right? So the question, there's some speculation is, did birds, I'm sure dinosaurs must have had four-chambered hearts, right? Because why would crocodiles have evolved four-chambered hearts and birds and not dinosaurs in between? But one of the big questions is, were they ectothermic or endothermic dinosaurs, right? And what do you think?
You said some dinosaurs had feathers, didn't you?
Okay, that's what I'm thinking. Is kind of, I just can't imagine you being in endotherm with all the additional costs in terms of how much food you need to eat without having involve some kind of insulation.
Could it be both? Ecto and endo, if they needed to be?
Oh, like facultative, like
Yeah.
they can switch between?
Yeah.
I don't know. Or I can think of maybe not one individual being involved, but there was lots and lots of species of dinosaurs. So maybe some lineages of dinosaurs maybe evolved here and not back there. Or
Like the Jurassic World dinosaur, you know, the one they made where they have a body temp on the heat finisher.
Oh, I don't remember that. So like when they scanned it and it
Yeah.
was,
There's nothing.
Endo thing? Endo?
Yeah.
well, it didn't have a body temperature or the body temperature matched the background.
Yeah.
Yeah, so I
Where
didn't
does
show
it
up.
go?
So
So
they
what would
like
that,
searched the cage and they're like, oh my gosh, it's gone. And they went in there and then it was actually in there.
okay, so that would suggest endotherm or ectotherm.
Exactly.
Ecto. Because they call this poikilotherm. That means you basically approximate your environment. Okay. You would basically be the same here. And again, the reason that we can maintain something different is because, well, I mean, some of us don't have a lot of insulation, but certainly our ancestors would have had insulation. But yeah, endothermy is so it's very expensive though, because you read these estimates. Remember, I used to keep snakes in here. Everyone's freaked out because like, you didn't feed the snakes today. No, snakes don't eat every day. Snakes barely need to eat hardly anything. I've seen estimates of these big giant Japanese giant salmon can eat like 1 or 2 fish a year, and they're totally fine. Right? They don't eat a hamburger and then burn it all up all that goes up the chimney.
Well, they don't move a lot, do they?
They don't move a lot.
I think you think that's why they only eat so little, because they have nothing.
They're in cold water, right? They don't move around a lot, and they don't waste their food energy on maintaining body temperature.
They don't have predators either.
Not, there's a few, but not many. Not, pretty much they're the top dogs. Once they get to a certain size, nothing's gonna mess with them.
I found that out about turtles too.
Turtles.
Yeah.
Turtles are amazing. They're one of the longest lived animals on Earth.
I know I had a turtle and I thought I had to feed it every day, just like a dog. And the funny thing is that it sat there, like in
And
the
it
bowl.
couldn't, probably got to the point where it couldn't withdraw to the shell. It's a little,
It had trained me. I was like, oh, you're hungry.
yeah.
No.
Okay, so here's the modern extant birds, and we see some of the sort of lineages leading up to the birds. This would be the Caudipteryx and Archaeopteryx. Well, actually, Archaeopteryx was very bird-like. This is the one that had feathers, for sure. Feathers all the way down here, though. But again, we see these skeletal similarities with all these reptiles and birds.
Do you know the predatory bird back in like the prehistoric? And then I keep forgetting the name. It was a terror bird. You know,
Oh, the terror bird.
yeah, and it looks just like the shoebill sort. You've seen the shoebill before?
Oh, starts with a Q?
No, shoebill. Shoe.
Oh, shoebill, they have those big. Oh, well, so these were flightless birds, right?
Yeah.
See, there's even a whole family. This is the amazing thing. Who the heck knows what happened on this earth before we were here, right? Now, some of these, I don't think terror birds, but there were some of these things called moas that lived in New Zealand with modern humans, and they were like bigger than modern humans. Like obviously this thing was a predatory flightless bird. Unbelievable, just unbelievable. So what does this suggest? I would guess this lives in a place where there was not a mammal building its niche. I don't know that this thing could compete with a wolf or something.
It only has legs. Pretty much.
Right.
So.
Yeah, I mean, given, I would probably put my money on this over this,
Okay.
but if we don't have machine guns and stuff, I mean, really, how badass are humans? Think about it, man. Humans are pretty weak. You got these little fleshy innards just sitting right here waiting to be eviscerated. I mean, we're not really, it's the intelligence that really benefited us. Terrible. Okay, I gotta focus. Okay, so flight, you know, this one, in some ways, it's kind of, the thing about evolution is you can see the benefits of feathers for a flightless bird. You can see the benefits of being able to fly if you have fully functioning like a barred owl or something. The question is like this in between. What are the intermediate steps where we go from having our forearms sort of turning into being modified into wings, right? And feathers being full blown for flight. But how do you describe these intermediate steps? Right? Why would a pseudo wing be better, more beneficial? Because that's the thing. Natural selection only favors things that are beneficial to your reproduction. Not even just survival. Because you can survive till the end of time. If you don't have any babies, you don't have an impact on evolution. Okay, so this, you need to be able to explain this as that basically, and how the wings became, turned from, a forearm like this into wings. It's just the genes, right? Developmental genes that turn on, this bone gets bigger, this bone gets smaller, these bones fuse. But the question though is the why. Why would selection push development in that direction? And I think that these are pretty good, two competing hypotheses. One is that if you were an animal like these dromaeosaurs, and you made a living by running down your prey. Obviously, they're bipedal, and they have these raptorial front forearms, right? That if you're running, how do you become faster? Is you become lighter. You overcome gravity a little bit, right? And that's going to allow the thrust forward to make you go faster. So what's one way to get lighter is you basically use your forearms to glide a little bit, right? You guys ever have a dream like that you can kind of fly like that? Not flying, but you can really lightweight. You can just imagine you can tie some like balloons on you and probably could run faster, right? So that's one hypothesis, is that the in-between stages can be accounted for by gliding, okay? And that as they were better and better able to glide, eventually that sort of turned into powered flight. Okay? Alternatively, or no, that's light running. I'm sorry, that's light running. Gliding would be that you're an arboreal organism, and that just like our flying squirrel here, right? Our flying squirrel is not.
It's right.
Okay, yeah, it's not powered flight. This thing obviously is beneficial to be able to get from tree to tree without coming all the way down on the ground, right? You're in a tree, there's a predator, you can just glide over to here, okay? Rather than being, you ever watch a gray squirrel on a tree that's about to get eaten? You're kind of scrambling back and forth, going up and down. Oh, this thing just bails out. It just jumps off the tree and glides over. So that you can see where the ability to glide would be adaptive, right? And that would create a selective pressure for bigger feathers, would create a selective pressure for changes in your forearms, ultimately could potentially lead to power flight. And then the light running was the first one I described. 160 million years ago, right? I'm looking over here. That was, still, I took Keith in here yesterday, and I was like, showing him that. Even Keith, he wouldn't admit it, but he was pretty amazed by our discoveries that first eukaryotes way the hell over here. First animals, first chordates. Right, so then would have been way over here that we would have had the first bird. Birds are a pretty recent addition to the vertebrate fauna, right? 160 million years ago. This is sort of the classic intermediate fossil between reptiles and birds, but this is kind of outdated. There's a lot of, particularly coming out of China, there's a lot of really amazing dinosaur bird interface fossils. Totally feathered dinosaurs. They can even tell by the fine structure of the fossils what color the feathers were. Right? Amazing, the kind of information we're getting about this transition. Okay, so suffice to say, poof, there's modern birds. Here are some of the sort of bird-like characteristics. And you should know this. I'll put a list of the ones that you should know from this. Okay. But I realized this the last time I taught this. I started asking people, like, for example, you guys know what what's this from?
Under.
Nope. This one.
What is it? Hang on.
How about this one?
Hang on.
femur. Okay, femur's on the leg, the humerus
Hmm.
is the arm, right?
Cause it
So
ain't
that makes these two here,
radius and all.
the radius and ulna. Now, okay, humerus, so this should be the blank and the blank,
Tibia and fibula.
tibia and fibula. Now you see that this just becomes like this weird little splint of the bone. Now what the heck is this then? 1, 2, how's our extra joint here? And think about birds, the way that their knees bend. The knees don't bend like this. They bend totally the backwards because this is not their knees. This is their knee up here. This is basically foot bones that have become elongated into another segment, another joint. Okay. That's a good point.
The bone right there, 15. What is it?
Okay, number 15.
Like a big,
Okay, yeah,
like a big, whatever it is.
the sternum. So when you eat chicken breast, they're split chicken breast, they split here. That's that little bit on the end. A lot of that is cartilage that you end up eating, or you don't eat, you peel away from. If you guys are vegetarians, I apologize. That is the sternum. And why is it so keeled and why so long? Sticking out like this. It's like in a dog's skull. Why is there a big ridge at the top? Like the trochanters, why are there little things poking out? Just like the spines sticking off of a vertebrae.
Aerodynamic, muscular intelligence.
Muscular, yes. And think about it. What muscles attach on there? If they contract, what happens? These muscles contract, what happens? The wings down. Some of the biggest. So in some birds, 20 to 30% of the body mass come from those muscles alone. Right. Sternum. What do you notice about the vertebral column that's different from like a mammalian skeleton? The vertebral column. So basically, the pigostyle all the way up.
We ain't got that big, unless you got scoliosis.
Okay, so number one, look at the neck. These are cervical vertebrae. All right, that part is movable and flexible. What about the rest of this? It's pretty shortened, and it's very fused, very rigid. And you kind of see if you look in this Chuckwell's widow here, you can see down there and see the vertebrae. They're fused together. Okay, but would that make sense? Because when you're flying, what do you not want to happen is you don't want to be flexing like this. You don't want to be losing all of your energy because your backbone is just like a noodle, right? You don't want this, right? It's like if an arrow is too flexible, you lose all the energy from the bowstring. You want it to be rigid, right? So that's the case with vertebral columns. What about the skull? Very lightweight, reduced bones, right? Where's the center of gravity going to be in this organism? Right underneath the wing. Right? You don't want a bunch of heavy stuff back here and a bunch of heavy stuff in the front. You want the force of these muscles contracting to transfer directly to the wings. I'll be lost in all this rest of this. And then these are pretty elongated. Right, those forelimbs are pretty elongated. That makes them have a lot of surface area. Because we're going to see that's where the flight is achieved along those bones there. Okay, so make sure to, let's see. So this kind of explains, right, the long ulna is about increased wing area. The pigostyle, that's number 9. These are a bunch of fused vertebrae. You don't have a long tail like you would in mammals or reptiles, they're fused into this little thing called a pygostyle. The halix is basically backward point, this guy here, backward pointing toe, which allows birds to grasp things. Here's that sternum, keeled sternum, right? It's about the pectoralis muscles attaching. We'll look at these coracoids and furcula here, but then the shortened vertebral column. Okay. Let's look at the coracoids and furcula. Okay. What are we looking at here? Which part of the organism are we looking at? Yeah, we get the wishbone. That's right, in honor of our Turkey Day forthcoming. That's the furcula. But where do you find that on a bird?
Honestly, I think I know that.
On the chopping block, right? After grandma gets done.
Yeah.
Yeah.
Looks like in between on the wing.
Yep. Pectoral girdle here. Okay. Because what is it that's sort of telling you it's the wings?
Got a humerus scattered.
Okay. There's the upper arm bone. Okay. They attach. This would be basically the scapula or the sort of the like shoulder blades, right? Here's the sternum, right, coming up from the breast, and so the furcula and the coracoids are related to a lot of the skeletal specializations of a bird are related to this flapping flight. Right? It's about, it's really a lot of it is about stabilizing this joint because there's a lot of force involved here, and so this needs to be a very stable motion. Okay, so the coracoids are about, well, we'll see that particularly the furcula is about stabilizing all this. Okay, so we said here's the pectoralis muscle. When it contracts, what's it do? Pulls down on the humerus when it comes down. What about this muscle?
Pulls it up
How's that work? There you go.
by that fulcrum right there.
Okay. So it goes, this muscle shortens, and because it goes up over the coracoid, it basically creates a fulcrum. And when it pulls down, it actually pulls because this tendon is attached to the top of the humerus, it creates the upswing. This is different. Most of the time, where would you expect this muscle to be attached that's pulling up? How does our wings back? When you work out, what does this motion work? Well, I'm sorry, not this motion, but this motion. Your back muscles. You usually have these antagonistic muscles, one on the back that pulls, one on the front that pulls this way. Totally different system, right, with birds. They're both here on the ventral side. And so the coracoid creates the fulcrum. Right, pretty neat system. Okay. The size is 17 feet. Look at this is their forearm. That's the humerus. The radius and ulna. Okay. A bit about feathers here, and right, they're made out of keratin. You can see. Did I put the? This is a scanning electron micrograph showing the fine structure of these. So we have the central vein. We have these brachies that go out, and then little barbules coming off of those. And then even these guys have a microstructure, these little hooks. What do those hooks do? Yeah, so I'm looking for a feather. I wish I had one that wasn't on a bird. biologist. Okay, but if you guys, I'm sure you guys have all played with vets, right? If you can see, like, you do like this, oh, the thing is ruined, right? Not so. When you get back like this, it all starts to connect back together. Right? That's because of those little barbules. Yeah, this would be probably the tailpipe. So that gives, right, it's all about, why is that adaptive for a bird? To be able to maintain a smooth surface. Airflow over that surface, you want it to be non-turbulent. You don't want it to be broken up. You want it to be streamlined, smooth. Okay. Now, wing flight. So I'm just gonna let's see. I have a couple of minutes. I'm gonna try to explain this. Okay, so okay, everybody stand up and let's think about pretend you're a bird. Everybody stand up. So how do you think a bird, when a bird is flying, what is the bird doing? Like, what's the motion of their wings? Are they just flapping like this? Okay, are they going? So here's the thing, like, why would this create any thrust?
Yeah.
Here, if you're just flapping up and down, what does that do? It's just moving the air up and down, right? But what do they have to do? They have to create thrust forward. So do they do some kind of motion, right? Like this, because it needs to create, yeah, that's it. But they're not going like this, because you think about it, if you're swimming through the water, you have to push the water back. So somehow they manage to push the air back, right? Okay, you can sit down.
What do you think if they were to come up like that, little, like stop in midair?
Right, because then that creates drag too, right? So here's the motion, and I would encourage you guys to read this part of your book. I feel like they do a good job of this. So here is a bird, obviously. There's a bee, right, of course. So this shows you the movement of the bird is forward, the movement of the wingtip relative to the bird. As they stroke down, it goes forward, just a little bit. It goes down, right? And then they come up, and it goes down. And it goes down, right? And if you watch them in slow motion, you can kind of just see it. You ever see these videos of like a goose or something flying in the air and it's sort of beside it? You can just see the wingtips moving ever so slightly. They do kind of do like a little bit of a circle.
That's what I was doing on the beat too, because it helps the wind.
That's right. It's like bump draft and then NASCAR, right? In fact, when the wing comes down, right, you think about it, you're displacing the air. That air goes up, and if there's another wing right here to catch that up.
Like a slipstream.
Huh?
Like a slipstream.
Yeah, like driving next behind a tractor trailer or something. So here's the things so you've got drag pulling back, you've got gravity pulling down. The bird needs to create two forces in order to fly forward. One, it needs to create lift. Two, it needs to create thrust. Okay? And we see that the generally speaking, the thrust is created by these feathers, called the primary feathers, on the end of the wing. Okay? Thrust created here, lift is created here. Okay? The lift is pretty easy. I think the lift won't make sense. You guys know about the Bernoulli effect? Right? How does it, everyone's flying on an airplane, it's kind of like, wait a second. This big, huge piece of metal is now just going to go into the air? The hell, right? You don't think about it too much when you're up in the air because you don't really freak yourself out. How does that work?
Yeah, it's like a.
Okay, so that's creating thrust.
And they have, like on the back of the wing, they have like a little.
Okay, it has a little flap. Right? So it's the shape of the wing. The shape of the wing is what creates the lift. So what, so it's shaped like this in cross section. And then they have a little flap that comes down too, that can create an even more pronounced shape like this. As the air moves across the wing, hits here in the same time, right? This wing, this air here, and this air here meet here at the same time. But because this air on the top of the wing has to travel further because of this curve, it has to go faster. Okay?
Oh, that's one that whenever the flap goes up, it travels, the plunges up, and then the flap goes up.
Yeah, so that what the flap does is it makes the contour longer so that that as the air travels over, it needs to meet its friend. It's like square dancing, right? Go, see, go, and then we go, and then we meet here. You gotta go faster to meet long air at the same point. As this moves faster, it creates negative pressure and it creates lift. Just about the shape. The shape dictates how fast the air on the top and the bottom of the wing move, and that creates lift. So the contour created by this edge of the humerus and then these feathers creates the lift. Okay, I think that one's pretty easy. And I don't think anybody really understands how the primary feathers create the thrust. Okay. So again, here's the shape of a wing of a bird or pear, airplane or whatever. So again, because it's cambered like this, the air is moving fast. It creates a lift. They can also change the relative position of the wing in the body, right? So because they can, this is a movable ball socket drawing. They can move their wings from like this to like this, which creates even more pronounced lift, right? But it also creates a lot of, what's this stuff? This is turbulence, which creates drag, which pulls back the bird. Okay, so they have these adaptations. This little thing called the allulose, little feather off of the humerus. That this is kind of like a spoiler on a car, right? In that it basically smooths out the air and makes it slotted, and then creates a lot less turbulence. Okay. And we see this because of the weather of the feathers are all independent of each other. It creates a lot of these little slots and it reduces the turbulence. But somehow those primary feathers, when the downstroke of the wing, the primaries twist a little bit, and when they're moving forward, it creates thrust backwards. I'm still, and scientists have studied this in amazing detail, looking at these wind tunnels with the little smoke in there, looking at where the air moves. It's not really fully known, but suffice to say that this slight forward motion and downward motion of the primary feathers on the ends of the wings create the thrust, and then the air moving over the top of the secondary feathers creates the lift. Okay. That's magic. If you can explain it, then I encourage you to do so. I will put the rest of the bird lecture up on Eagle Web or Canvas for Friday. Okay. And then we'll cover mammals on Monday, and then the exam 2 on Wednesday.
Dr. Steele,
Yes.
have you ever seen a shoebill stork before?
A what?
A shoebill stork?
No. I think that's an African bird, isn't it?
It is.
Is it? And why the beak? Why the beak? Like, what's it adapted for?
For eating fish.
Oh, is it? They're fish eaters?
Yes, sir.
Okay.
What's the word? Isn't that like, no, what's the word for, what's up, Dad? What's the word for eating fish?
Oh, piscivorous.
Piscivorous, yes.
Yep. See ya.
See ya.